Okay. So I I updated all the grades. Yeah, I have the exam already, the exam grades in Canvas. I also have the wiki grades. Everything is updated. Now let me know if you have any questions. I also added a quiz, which is gonna take care of some extra credit for exam one. So I label it like that: quiz 4, extra credit for exam one. It really is one problem assigned at random by the system from section E, which is the one that we're covering right now, inclusion exclusion principle. Now, it's this Saturday, anytime on Saturday. You can get started whenever you want, but you once you open it, you have 1 hour to do it. So you can go over some of the problems and section E, have an idea or have plan or have notes if you want, and hopefully the one that assigns to you already tried, and so it's going to be easy just to write down what you had. If it's one that you haven't finished, you still have an hour to complete it. Make sense? It's just one problem, and it's an upload, so you to do it in paper, take a picture, that's it, upload. Okay. All right. And then we'll have more. But this is the starting point, and this is for this weekend so that you can practice with this section. And since I will get started with graph theory today. All right.
Question: how is that extra credit work? Is it going to be added towards the exam, and is the exam going to be worth 110 instead?
No. So the exam, you already have your grade for the exam. So whatever you have, let's say if somebody has 70 in the exam and you get the full extra credit for this quiz 4, that would be 10 more points. So it would be an 80 instead of a 70. Make sense?
Could you explain that just one more time, how the extra credit's going to go? Sorry.
Just whatever number of points you get in the extra credit, you add to your exam grade.
I see. If I got an 80, then it'll be, if I get a good job, then I'll do 90, basically.
Yes.
Okay, I see.
Yeah. They go directly to the exam. Right? And everybody is welcome to that, because I was going to do wikis instead, but there aren't enough problems in that section. So, and I didn't want to exclude anybody. I think whether you did good or bad in the exam, everybody deserves to get that extra credit. So, and it's up to you. You have time. If you did really well and you have time, then you can try it. If you don't care, then let it pass. Yeah. Anyways, so let me get started where we stop for inclusion exclusion. Let me share. I'm just copy pasting what we had at the very end last time so I can show you. Okay. So this was my very first slide last time. What did you get for this one? Did you try this exercise, the D4? I mean, of course, you got mine, but how was it? Did you get them all? Do you understand what the derangement is? Okay. So, how do we prove it? Yeah. Let me just move this to the next page. So, first, remind you, so derangements are rearrangements of a string that do not leave any element in its original place. Mm-hmm. So we want to prove this formula using inclusion exclusion. I'm just going to move it to a different page so that it's clean, and we'll get this started. Okay, so here we go. Remember that for inclusion exclusion, we define some sets AIs, and then we're going to take the size of the AIs and then the size of the double intersections, the triple intersections, and so on. And when we subtract from the total alternating sums, that's essentially inclusion exclusion. So usually the hardest part of these problems is, especially for you guys, you already have experience with algebraic manipulations and all that. The hardest part is the combinatorial part of it, which is deciding what the AIs are going to be. And so, because the arrangements, because of the definition of arrangement, you have for the n, let's say, you have strings using the numbers 1 through n. You can think of it like this. You have strings using the numbers 1 through n. And a derangement has to move 1 away from the first position, 2 away from the second position, and so on. So it doesn't leave any number in its original position. So actually, let me first, my universe is going to be all the rearrangements of the word. So U is going to be the rearrangements of the string 1, 2, 3 all the way to n. And the AIs are usually whatever you want to avoid. So for each I between 1 and n, I'm going to define AI as the rearrangements in my universe that fix, what I don't want, that fix I. Those are not arrangements. That's what we're trying to avoid. So the issue is that we have to avoid that for every I at the same time, right? But when we just focus on one of them, we actually make it easier. The counting is easier. So those are our AIs. And then with the notation that we were using before, everything from here, if these AIs work, then everything from here should be a little easier. Of course, we're going to need our counting techniques from the previous section sometimes. But from here, you want to know what is 0. That's just the size of the universe. So that's just permutations of n elements. That's just n factorial. And then in order to find S1, I need to find the size of each AI. Remember, S1 is the sum of the size of A1, the size of A2, all the way to the size of AN. And so I need to figure out what is the size of AI. And the way that we do, in most of the problems, there is some symmetry, like all the AIs behave the same way. And so you can count for 1 and then just multiply for however many you have. And so AI are the ones that fix I. So, I have that, I fix the I, and then I kind of keep working. So the I is here, and everything else is a permutation. So now I only have to permute n minus 1 elements. So it's n minus 1 factorial. For example, the ones that fix 1, I have the 1 in position 1, and I have to permute the rest. So that's the n minus 1 factorial. So this one is just n times, because I have n terms, n minus 1 factorial. And then S2 is the sum of I pick 2 subindices at a time, and I do AI intersection AJ. And then this one is, AI intersection AJ. If you think about it, is this time you have the I fixed someplace, and then you have the J fixed someplace else, and then all the others need to permute. So I and J don't move. So now I only have to permute n minus 2 elements, right? And so it's going to be the same for any pair. And I just need to count how many terms in that sum I have. Let's then choose 2 because I'm taking an I and a j, any pair. So this is the number of pairs or terms in the sum. And then I multiply times that n minus 2 factorial. So that comes from here. Yeah. And then we can compute S3. So this is the set of triples. 1 less than or equal to I, a j. I take an I, a j, and a k. And then I take the intersection of those. AI is the set of rearrangements that fix I in its original position. AJ fix J, AK fix K. So now I'm going to have the I fix, the J fix, and the K fix. And as you can see, I'm going to end up with only n minus 3 elements that have permit. So the intersection of this is just n minus 3 factorial. And I do the same as in the previous one. I count how many terms. I'm just choosing 3 elements, the I, the J, and the K. And each of those cardinalities, each of these terms is equal to n minus 3 factorial. And so I can keep going like that. I have the SK, if I keep going, SK will be, the notation is going to look ugly, but one way to do this is to say the intersection of A1, A I sub 1, A I sub 2, A I sub K. That just means that I'm taking K subindices. And here I can say 1 less than or equal to the first subindex, less than the next subindex, less than the last subindex, less than or equal to n. And so I know how many terms I have. I'm just choosing k subindices. But then I need to multiply times this, right? And so in that one, we're fixing k letters, right? Or k elements in their original position, right? Which means that that cardinality, we only permute the rest. So that cardinality is the rest of the elements factorial. So here we have n minus k factorial. And the largest intersection we can have is the one with all of the elements. So, the last of these S values is Sn. Sn is simply the intersection of all of them. And so if we're fixing everything, that would be 1. And in fact, notice that this actually fits our formula. It's using in the previous one, k equals n. Gives you n choose n times n minus n factorial, which is 1. So this S of n also fits this formula right here. But, just to kind of complete my list. Okay, and then the inclusion-exclusion principle says to just add all of this alternating signs, right? So we can say then, by the inclusion-exclusion principle, the number of derangements is equal to S0 minus S1 plus S2 minus S3, dot, dot, dot. And we always have, since we're alternating signs, that's just going to be, the very last term. Maybe I should write one term in the middle, like the general term. And then the very last one is just going to be that one. Mhm. So you can write this as the sum from I equals, I equals 0 to n of s, well, actually, let me do k. K equals to 0. So it goes with my general term. So k equals 0 to n of sk. And we have that this is n choose k times n minus k factorial, which, by the way, this formula right here also fits this ones. Let's see. Let's just make sure, because maybe it fails to fit the first one, because the first one was computed in a slightly different way, I guess. So, but for the first one, when n is 0, when k is 0, we have n choose 0, which is 1, and then n factorial. So it's okay. It works for k equals 0. For k equals 1, it will be the n minus 1 factorial, and this is n choose 1, which is n. So, it works even starting at 0. And just, looking back at what we wanted to prove, looks like this. So I'm going to expand my binomial. There's no binomial here. So just to reduce it to that form, I'm going to expand my binomial. K equals 0 to n factorial over k factorial times n minus k factorial. Oh, wait, I'm missing, sorry guys, I'm missing the alternation, right? And maybe I'll add it here. Negative 1 to the k. I expanded the binomial. And so now this cancels. The n factorial doesn't use the mute variable for the sum, so I can take it out. It doesn't use k. So this becomes n factorial, the sum from k equals 0 to n. Oops, what am I doing? N factorial goes out of the sum, and now we only have the negative 1 to the k over k factorial, which is what we wanted. Questions? So this is like one of the harder problems, I guess. I think there was this one. Yeah, so this one is a theorem, but it was one of the problems in it's E37. So, but it's one of the harder ones, because most of the problems in that section are actually not in terms of another variable, like a variable n. Most of them have specific size strings, or in principle they're more tangible, because you only have, instead of having like n sets here or n sets there, you only have 3 or 4. Questions?
Maybe it's just me, but this seems really overwhelming.
It's okay. It's okay. Again, this looks more overwhelming than other examples. Let me show you others that have at least a tangible number of sets, 3, 4, 5 instead of n. Here we have n sets, and that the notation makes it overwhelming.
Like, I know if I got that question for my extra credit, I probably would not be adding money.
Yeah. So that one is not part of the extra credit, or neither E38. E38, I guess it's a curiosity because, for people who are interested in how fast is the function Vn, the arrangements function increasing. Maybe I'll go back to this. This over here. I asked you last night, like, if this reminds you of something from calculus, this series. If you make it all the way to infinity, this is E. So, I'll add it right here. So E38 is asking you to find the limit. Let me make it a little bit smaller. So E38 asks you what is the limit as n approaches infinity of Vn over n factorial. And because you have the formula here for Vn over n factorial is the limit as n approaches infinity of the summation from k equals 0 to n of negative 1 to the k over k factorial. And this is just, in the limit, this is just a series. From k equals 0 to infinity of negative 1, an infinite series. And this infinite series should remind you of something you saw in calculus when you saw series, the exponential function, the Taylor series for the exponential function is looks like this. This is, and let me just make it clear. That's a k, and this is x to the k. So that's a function to the x. This is the Taylor series of the exponential function. And so if you use x equals 1, so e equals e to the 1 is just that series that you wanted for our limit. So this is just e. So for, not many of you are computer science majors, but for example, for computer science majors, it is important to know how fast the function grows. And so the rearrangements function, this over here, is hard to know how far it's growing. Is this exponentially growing? So does this behave like a rational function, or is it more like an exponential function? So what is it? And so this is telling you that the n grows very similarly to n factorial, just by a factor of e. Yeah. So for many people in combinatorics, depending on what you do, this is an important fact, just to estimate how big the dimensional numbers are. So now you know that E36, E37, E37, E38 are not in the quiz for extra credit. Going towards what I was saying, more tangible problems. I'll upload this. I know that maybe you didn't finish copying for E38, but I want to show you the other problems that are, I think, easier. This one is E9. Let's see, I have a list someplace here. So 42 and 40, problems 42 and 43. Yeah. So, when you practice for that quiz, you can probably use this. So E9 says, find the number of positive integers of 100 that are not divisible by 2, 3, maybe I should say by any of 2, 3, and 5. Yeah. So, for example, just to try to understand the problem, you have the integers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you keep, all the way to 100. And you want to count 1 because it's not divisible by 2, 3, or 5, but you don't want to count the even ones, right? Because those are divisible by 2. You don't want to count the multiples of 3, so maybe I should do this. You don't want to count the multiples of 3. And you don't want to count the multiples of 5. Yeah? So, you don't want to count the multiples of 5. Yeah? So, counting the multiples of 2 just by themselves is easy. Those are the even ones. It's 100 over 2. That's 5. Counting the multiples of 3 is easy. It's about 100 divided by 3. Actually, the floor of that, so 33. Counting the multiples of 5 is easy. That's 100 over 5. That's 20. I'm going to write all of this. But just to, counting some of the things that you can exclude is easy. So in my list, the 7 we should count. So counting what you want to exclude. So remember that inclusion exclusion is like the generalization to that complement idea. From everything I subtract what I don't want. So subtracting the multiples of 2 is easy. Subtracting the multiples of 3 is easy. Subtracting the multiples of 5 is easy. But then I'm over subtracting because if I just do that, the number, why did I have the 3 cross out? Give me 1 second.
Like some 10 gets out twice and 3 gets out twice. And
Exactly. Let's see. For the 3, I should only have crossed it with red, I guess. 2 and 3 were crossed out only once, but 6 was crossed twice, right? And so if I just subtract them, then I have to make up for that. And that's exactly the idea of inclusion exclusion. So let me set it up with that, right? So we're going to use inclusion exclusion. So what are going to be my AIs? Well, remember, U is going to be everything. It's just the set 1, 2, 3, and so on. So that's my universe. I want to subtract from that. So I'm gonna make A2, A3, and A5. The multiples of 2 in my universe, right? So 2, 4, 6, all the way to 100, the even ones. A3 are the multiples of 3, between 1 and 100, less than or equal to 100. And A5 are the multiples of 5 that are less than or equal to 100. Yeah? So remember, my A's are my exclusions, but those are easy to count by themselves, but now I need to combine them. This is the principle. So what is 0? S0 is a cardinality of U that's just 100. S1 is A1. The cardinality, no, there's no A1. A2 plus A3 plus A5. And it's actually very important. It doesn't sound like, it doesn't have to be A2, A3, A5, but if I use A1, 2, 3, then the rise of index doesn't say anything, right? So using the rise of indices is actually helpful, so that the subindices tells you something. So I need to know that. And the thing is that, what is A2? we said it's all the events between 1 and 100. So I can essentially divide by 2, and that's it. That's 50. Okay? And A3 is almost the same thing. I just divide by 3. But the last one, 100, 100 is not a multiple of 3. So I could as well have done 99 divided by 3. So that's the same as taking the floor function. So this is 33.333, and you take the floor function, that's 33. And then A5, that one is actually also an exact division, so that's 12. But if it's not exact, just take the floor. So S1 is 50 plus 33 plus 20, which is 103. And of course, if we subtract that from 100, we did and that's it, we did something wrong. So that's because we subtracted too many. So now we need to add them back. But we're going to see that when we apply the principle. So now we need A2 intersection A3 plus A2 intersection A5 plus all the intersections. There are 3 of them. And, all our combinatorial skills so far tell us how many terms we have so that we can double check. And these are the pairs we choose to, the 3 pairs. And to figure out what are the sizes of those, A2 intersection A3 are actually the multiples of 6, right? They need to be multiples of 2 and 3 at the same time. So this is just going to be 100 divided by 6 and take the floor. And for A2 intersection A5, that's multiples of 10. So that, which is 10. This one is 60, I think. So these are multiples of 10. And then I have A3 intersection A. Which one am I using? 5? Those are multiples of 15. Six of them? Yeah. So S2 is equal to 16 plus 10 plus 6. And then the last one is S3, which is just the intersection of all of them. These are the multiples of 30, 2 times 3. Because these numbers are relatively prime, is just the product. So multiples of 30. So this one is 100 divided by 30. The floor of that's just 36 remaining. And then we use inclusion exclusion. What we want. I'm just gonna, this, what we want is equal to is 0 minus S1 plus S2 minus S3 equals 103 minus 32 plus 3 minus what? Let me see. No, wait, sorry. I forgot my S0. So 100 minus 103 plus 32 minus 3. 26. I did something wrong. What did I do wrong? Well, hopefully I added everything correctly. If you find a mistake in my computations, please, just let me know. But it seems it's okay. All right?
Professor? for problems like this, I think it was easier because it was all odd numbers. But let's say if we are looking for multiples of 2, 4, 6, the cross will be, we'll have to find each term, right? For like S2, cross between A2 and A4 will be, I guess, technically the A4 cardinality
Yeah.
of A4. No.
Yeah, that's a very good question, Shin. Where you're gonna see a change is when you count those ones. For those ones, it's gonna be the same, right? You can call them 2, 4, 6, and they're gonna look the same. But then when you combine them, you need to figure out what this means. In this case, let me just write it here on the side. As if you had A2, A4, A6, same problem. Numbers between 1 and 100, not divisible by 2, 4, or 6. The thing is that when you do A2 intersection A6, these are multiples of 2 and multiples of 6 at the same time, right? So what does that mean? Well, multiples of 2 and 6 at the same time. Every multiple of 6 is a multiple of 2, right? So this is just multiples of 6. One is containing the other. So it's because it's the intersection, it's just the multiples of 6. And so once you know this, you can do 100 divided by 6 as before. So it's not always the product. It's what's going to change is the interpretation. What is multiples of 2 and 6 at the same time? The interpretation will give you a different thing here, and that's what you will do. Same thing when you do A2 intersection A4 intersection A6. What does it mean? It needs to be a multiple of 2, of 4, and of 6 at the same time. So we like the
multiples of 12.
Yes, the least common multiple, that's 12. Every multiple of 12 is multiple of 2, also multiple of 4, and also multiple of 6, and vice versa. Anything that's a multiple of these 3 is a multiple of 12. So, multiples of 12. And so this would be 100 divided by 2. In general, if you want, this is just the least common multiple of 2, 4, and 6. When you have prime numbers, or not even prime numbers, but relatively prime numbers, like the 2, 3, and 5 that we had in the original program, you just multiply them. But if they have something in common, you have to kind of just take the least common multiple. It's going to be smaller than the product of the numbers. Make sense? But that's a good question. E42, as I said, E42 and E46, E42, E43 are like this. Okay. Okay. One more, maybe. We can try, for example, this is maybe E45. Yeah. So this one is like a mixture of, I do have a fixed number of sets, like in the previous example, 3 or 4, but I need to be careful when I look at the intersections, what's the meaning of the intersections. So in this one, it says, find the rearrangements, number of rearrangements of 1, 2, 3, 4, 5, 6, in which none of 1, 2, 3, 3, 2, 1, 4, 5, 6, and 6, 5, 4 occur. Okay, so that's what I want to avoid. So again, the first part is to get your sets U and the AIs correct. Right? So U is just going to be the rearrangements, your universe, right? So we're talking about rearrangements of 1, 2, 3, 4, 5, 6, no restrictions. And your A's are going to be your restrictions. So you don't want to have 1, 2, 3. You don't want to have 3, 2, 1. You don't want to have 4, 5, 6, and you don't want to have 6, 5, 4. Make sense? So this is elements of U containing 1, 2, 3. Like together, like 4, 1, 2, 3, 5, 6, like that. That one contains 1, 2, 3 there. Mm-hmm. And then same for the others. The definitions of the others, the ones containing 3, 2, 1, the ones containing 4, 5, 6, the ones containing 6, 5, 4. So that's what you want to avoid, right? And we do it that way because counting one by one is easy. Combining them, we need the inclusion exclusion principle. So the 0 is the permutations of 1 through 6. So that's 6 factorial. S1 is the sum of this. Mm-hmm. And we know how to use them. I mean, if you need to fix the 1, 2, 3, for this one, you will have the symbols 1, 2, 3, 4, 5, and 6. So you glue this one. Now you have 4 symbols, and so it becomes 4 factorial, the number of rearrangements. Make sense? So the cardinality of 1, 2, 3 is 4 factorial. You have 4 symbols, this one, right? 4 symbols. The 1, 2, 3 glued together, 4, 5, and 6. And the same for the others, right? So, instead of writing each one, it's just going to be the same. For 3 to 1, I just glue different elements. I glue those, and then I have 4, 5, and 6 here, and so on, right? So this one is just going to be 4 times 4 factorial. All of them behave the same way. Then I need the double intersections. 1, 2, 3, intersection A, 3, 2, 1, and all of them. A, 1, 2, 3, intersection A, 4, 5, 6, so I have 6 of them, right? Or choose 2. So A, 2, 3, intersection A, 4, 5, 6, A, 2, 3, intersection A, 6, 5, 4, and A, 4, 5, 6, intersection A, 6, 5, 4. And so I just need to understand what each one of these means. In the first one, can I have 1, 2, 3, and 3, 2, 1 at the same time? I can't, right?
Yes.
I can't. So this one is 0. Do you agree with me?
Yes.
Mm-hmm. And the same for that one, right? So those cannot happen at the same time. I cannot have 4, 5, 6, and at the same time 6, 5, 4. It's two different orders for the same. The three different orders for the same three numbers. That's not going to happen. For the others, I'm gonna do 1, 2, 3, and 4, 5, 6, and so I only have that or the other 2 factorial. Mhm. So all the others are going to be 2 factorial, 2 factorial, 2 factorial. We do 2 disjoint triplets, and we can just place them like 1, 2, 3, 4, 5, 6, or 4, 5, 6, 1, 2, 3. That's it. Mm-hmm. So S2 is, I'm going to write like this, 4 times 2 factorial plus 2 times 0. Just kind of to be explicit. When I have 6 pairs, 2 of them don't have any intersection, and the others have intersection of size 2 factorial.
I'm just confused on the last. There's a couple there that say just A23 intersection A654.
Oh, this one is supposed to be 1, 2, 3. No, sorry, 3, 2, 1, 2, 3, 1, 2, 3, 3, 2, 1. 3, 2, 1, 3, 2.
Okay. Okay, yeah, I was trying to just figure out the difference because it looked like the same thing written twice.
Yeah. So
Okay.
all the pairs, right? And in fact, I didn't really have to write them all. I can say, because I have the 1, 2, 3, and the, I could look over here on top and say, these two have no intersection, these two have no intersection. And then all the others have an intersection, like this one is like 2 separate pairs glued together. The same with that one, the same with that one, and the same with this one. There's my 6 pairs. The green ones actually give me 2 separate glued triples, and the red ones cannot happen at the same time. Mm-hmm. And then what do you think it says 3? These are triple intersections, but what's the size of a triple intersection?
0.
0. Always 0, right? Because I'm gonna have at least 2, like either these 2 together or these 2 together, and those never intersect. So once I add the third one, it's not gonna happen. So this is 0, and this 4 is also 0. So my number of rearrangements, let me just call it this. By inclusion, exclusion. That is equal to S0 minus S1 plus S2 minus S3 plus S4. And that happens to be 6 factorial minus 4 times 4 factorial plus 4 times 2 factorial. And you can leave it like this. Remember, I saw a lot of people in the exam were trying to reduce the D numbers and the S numbers and all that, and it takes time. For this one, you have 1 hour, which should be enough, but you don't want to spend time reducing things, just in case.
I just wanted to make sure you understand S3. Is it because you can't have like 1, 2, 3, 4, 5, 6, 3, 2, 1?
Yeah. So, for example, if you do 1, 2, 3, 3, 2, 1, and 4, 5, 6, let's say, then that means that you need to have these 2 at the same time, and that's impossible. And the other one, right? But even the first 2 is not possible at the same time. So that intersection is empty. Mm-hmm. And in any triple, you either have these 2 together or these 2 together. And so you're always going to have an empty intersection.
That's just because the elements outnumber the possibilities.
No, it's because can you give me an ordering of, here? Can you give me an ordering of 1, 2, 3, 4, 5, 6 that contains 1, 2, 3 and 3, 2, 1.
Gotcha.
That's not possible, right? So either I have the 1, 2, 3, but then that order is already fixed, but then I cannot have any other order of 1, 2, 3. I cannot have 1, 3, 2 either. One, yeah. Mm-hmm. So it's a matter of understanding what this means. We have the notation, but we need to understand what the intersections mean. That's, to me, the most important part is identifying the correct AIs, but we kind of always go by what we want to avoid. And the second part is the interpretation of the intersections. So really need to think what they are, what they mean, in order to be able to count them. Mm-hmm. Okay. Questions? So I'll do one more so that you have essentially like one example of, like for example, E45 can be helpful for, E45 can be helpful for, I had a list here. E44 way to E44, E46, they're very similar. So, you can practice and see if you kind of get the same thing. E48. Maybe even, it's a little bit different, but 33 to 36. Mm-hmm. Okay. So what I'll do is I'll give you two more examples, but I won't find the S, so that I have in the slide. I'll give you the A's and see if they make sense to you, and then we try to combine them to find the sizes, for the intersections. Right? So, oops. So, one of them is E10, which is helpful for E33. So E10 says find the number of distributions of 5 red balls and 5 blue balls into 3 distinct boxes. Did I want to do that one? Yeah, with no empty boxes. Okay? Okay. So, for our answer, so we're going to have U is going to be the number of distributions. 5 red, 5 blue, it was 5 and 5, yeah. 5 red and 5 blue balls into 3 distinct boxes. No restrictions. Mm-hmm. And then what I want to avoid is having empty boxes. I have 3 distinct boxes. So, I have 3 distinct boxes. So I can say that I have box 1 label, box 1, box 2, and box 3. They're different, right? So what I want to avoid is having A1 is elements of U, so distributions, those distributions in which where box 1 is empty. That's what I want to avoid, right? Having empty boxes. So A2 and A3. Same thing, but now it's going to be box 2 and box 3. Mhm. Mhm. So just remember that, for example, for oops, to figure out what's the cardinality of U, that's you just do the colors separately, right? So if I had 5 red balls, you do whatever you have for the red balls times whatever you obtain for the blue ones. Okay? So and what we have is identical balls. That's n equals 5 into different boxes. And we have 3 of them. No restrictions, right? And I'm talking about, just do it for the red ones and then do the same idea for the blue ones. So we're just going to square that. So this is n plus n minus 1, choose n minus 1. So in our case, 5 plus b minus 1, choose, let's do it like this. 5 plus 2, choose 2. Okay, so that one goes here. So that one goes here. And it also goes there because, now you do it for the blue ones. And then, I'm gonna leave this to you, but it says 1. There's gonna be something similar, but you're gonna use, instead of 3 boxes, you're gonna have 2 boxes because box 1 is empty, right? For each one of those. So for the cardinality of A1, the only thing that changes is that you have 2 boxes instead of 3. And when you have a double intersection, you only have 1 box instead of 2, and so on. So try to finish this. This is the setup. Okay. I don't want to do one of the problems that's in the quiz because that would be unfair for whoever, whoever doesn't get that one if somebody else gets them. So I want to choose carefully.
So how would you finish this one? You're gonna say S1 would be 1 empty box?
Yeah, for each one, right? Remember that here you
Multiply by
have
3.
A1 and then A2 and then A3. And when you compute A1, you only have boxes, you only use box 2 and box 3. So now your n becomes 3. Right? And so it's going to be almost the same as this one, it's going to be 6 just 2. Because your n changes. But then you have to multiply times 3 because you have to do it for A1 and then for A2, which is going to be the same computation, and then for A3, which is going to be the same computation. So it's going to be 3 times 6 just 2. Mm-hmm. So see if if this makes sense to you. Okay, complete the details.
Six choose 1 times 3 then? Oh, you did it. Okay. Um,
Okay.
Isn't it 1, Professor? 6 choose 1?
Oh,
Because
thank you.
is it?
Thank you.
Okay.
Yes. Yeah, because I have one list. Yeah. So the both of them go down. Oh, let me change this one as well. Go ahead. Oh,
So for S2 would be there's a 2 box empty instead. Okay.
there's only one way, right? For S2. But you need to be S2 is all the intersections. So how many intersections? Let me now read that. How many double intersections you have to choose 2? You only are using one box, so you can write it as 5 choose 0 if you want. But that's just gonna be one. This one is just one choice because you only have one box. You put everything into that box, so that's a one. Mm-hmm. But if you are looking for an explanation, it will be the same like this, but it goes down to, so here you're using n equals 3, here you're using n equals 2 for each one, and here you're using n equals 0, n equals 1 for each one, and this is the, for each one is the number of steps.
Professor?
Yeah.
What do you mean by the 7 choose 2 times 7 choose 2 for the blue balls and red balls? Because I see 5 red balls and 5 blue balls into 3 distinct boxes. So I'm just not sure about where the 7's coming from.
From here, I missed something else on the bottom. So from here, this is 7 choose 2.
Oh, for both?
For both, yeah. And in fact, that's a square, right? 7 choose 2 square. I also have squares here, because I have to do it for the blue ones and for the red ones. So I also have squares there. This square. Mhm. So, well, you know what? Let's just finish it then.
Yeah, you kind of lost me there.
Let's see this. Okay, I wanted to start with graph theory, but let me just finish this one. So, we did this, right? Did you get this one? So, I guess, let me clean it up. So this is the work for the red ones. And once you distribute the red ones, you have to distribute the blue ones, and it takes you the same number of ways. And so that's why I have this 7 choose 2 times 7 choose 2, which is 7 choose 2 squared, right? When I do S1, I need to find what's A1, A2, and A3, and everything is symmetric. So if I do it for A1, I'm gonna get the same for A2 and the same for A3. That's where I get these 3. There are 3 terms. So 3, and all of them behave the same. Now the 6 choose 1 that I'm getting here is also, if you want, for the red balls, right? And I need to square it because there's blue balls. And then for S2, I need to look at the double intersections. But when I do the double intersections, I essentially, let's say for this one as an example, when I do A1 intersection A2, box 1 and box 2 are empty. So you only use box 3, right? Because the other 2 are empty. So that makes it n equals 1. Same argument, but with n equals 1. So this will give you that 5 choose 0, which makes sense. And this is again for the red ones, right? There's only one way. Of course, there's only one way. I only have box 3. I put everything in box 3. That's it. There's only one way. And I square it. And this 3 choose 2, this 3 choose 2 is the number of pairs. You know, A1 intersection A2, A1 intersection A3, and A2 intersection A2. That's a 3 choose 2, which is 3. It's those 3. And for each one of those, we do the same work that I did here for A1 and 2. All of them give me the 5 choose 0 square, which is just the 1. And so I add those. That's why all of this is just a 3. And S3, technically we're supposed to get all the way to S3, but that's 0 because, all empty. All boxes are empty, and that's not possible. Right? This corresponds to A1 intersection A2 intersection A3. Again, what's the interpretation of this? The A1 is all the elements where the box 1 is empty. At the same time, box 2 is empty. At the same time, box 3 is empty. That's impossible. I don't have a place to put the balls, so that's 0. And then you just finish up with the inclusion exclusion. Let me do the same, just to avoid a little bit of writing. So if that's what I'm counting, so I can complete my proof or my solution saying by the inclusion exclusion principle, or just by inclusion exclusion, this is equal to S0 minus S1 plus S2 minus S3. S0 is 7 choose 2 square minus 3 times 6 choose 1 square plus 3 choose 2 times 5 choose 0 square minus 0.
I'm still not quite understanding that S2 with the 3 choose 2 out front.
Oh, okay. So S2, let me write it here. S2 is equal to A1 intersection A2, cardinality of that, A1 intersection A3, plus A2 intersection A3. Right? So 3 of them. And for each one of them is the same work. So this 3 choose 2 is just 3 equals 3 choose 2 terms. Right? It's just I have 3 terms. And for each one of those terms, I get 5 choose 0 squared. So you can, this is just 5 choose 0 squared when I do A1 and A2, plus 5 choose 0 squared when I do A1 and A3, plus 5 choose 0 squared, which are ones, by the way, but, in case you had larger numbers or something, this is how that will look like. Mm-hmm.
So is that value just going to be 3 no matter what?
It's because, yes, when you have 3 sets here, right? If I had 4 boxes, which, by the way, A33 has 4 boxes, right? The pairs, that's why I wrote it like this, because I could have said just 3 times, right? But if you have 4 boxes, then the pairs are going to be 4 choose 2. So you're actually going to have 6 pairs. So instead of 3, it's going to be 6. Mm-hmm. If you have 4 boxes, you have A1, A2, A1, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. 6 pairs. And still, they behave the same way and everything. So you just do it for one of them and count how many pairs you have. If that is an issue, you can always just, count the terms by hand. And the same thing as I was doing here, just write all the pairs and then just know it's 3. So, if you don't want to keep the binomials or anything, S2 is just 3 times 1 because we got 1 from here, and it's this is a 1 plus 1 plus 1.
Yeah, that's the way I was seeing it. So that
That's perfect.
was throwing me off.
Yeah, so that's perfect. I tried to write it like this because, again, when you have 4 boxes or 5 boxes or 7 boxes, maybe you don't want to write all the terms, right? You want to write this rather than this. Imagine 7 choose 2. It's 21 terms. Yeah, 21 terms. You don't want to write the 21 terms if the word is the same for all of them, So, but yeah, if you have, and that's why these exercises are a little bit easier because you can essentially forget about counting the pairs and all that. You just write them all and use the number, and that's it.
Thank you. Yeah, that helps.
Okay, good. Okay, so we couldn't start with graph theory, but we'll start next week. Please take a look at the beginning, like section A of graph theory. I'll show you how it looks like. I had it ready for today, but we didn't have time. So it's a very easy reading, I think. I don't know how many of you are familiar with graphs. Dots and lines joining them. That's essentially it. Vertices, those are the dots, and lines joining them. Those are called edges. But section A is mostly terminology. How we call everything. That's a vertex, that's an edge. When 2 graphs are considered the same, so these are just different drawings of the same graph. This equivalence graphs. I'm going to explain all of it, but I'm going to go very fast over this because, again, this is just terminology. So it will really, really help if you go over the section on your own. And then I'll explain it, but I'll do it fast because I want to spend a little bit more time on the exercises. And you see, all of these are definitions. All of these are definitions. So my plan was to essentially, we'll go over the book. I'll show you the pages. I'll try to explain, but if you're really ready, you can ask me, so I didn't get what happened here. And so I can focus on that little thing. But please read it because otherwise I think it's going to, I'm going to go very, very fast with section A. It's almost notation, names, a few little things here and there, but I want to focus on the exercises because section B is the one that usually gives trouble to people. Isomorphisms of graphs. I want to focus on that. Correct? Okay, guys. So I'll see you Tuesday. Have a nice weekend.
Can you see the end of the example real quick?
Yeah, sure, definitely. There you go.
Thank you.
Mm-hmm.
Well, I was late by like 3 minutes, so by the time I joined the class, you just stopped talking about the extra credit or something.
Yeah, so I have quiz 4. Quiz 4 is going to be extra credit. It's just one problem from section E, and it's an upload. So we're going to be, the quiz assigns a problem from section E at random.
Okay, and you say there were only 4 problems?
No, there are several ones. It's from E31 to E52. And you know what? I'll send you a reduced list of problems to study with.
Okay, because it looks complicated. I'm having a hard time understanding certain things, but hopefully in time, maybe.
Yeah. So, I'll send everybody a reminder, and I'll shorten the list of problems on the back of the book that I actually selected for the quiz. Okay. Okay. And whatever points you get in that quiz is out of 10. So whatever points you get in that quiz will be added to your exam run.
There's a quiz?
It is a quiz, yeah. So I'll send a reduced list of problems. You study those problems. Hopefully the one that you get, when you open the quiz, is one that you already solved. If you did, you can simply take a picture, upload it, that's it. If you haven't finished that particular problem, then you have an hour to finish it.
Okay.
Okay?
I was like, I saw my grade 36 out of 100, so yeah, I knew I did do well.
Okay. That's fine. Do that as the credit. I'll keep you updated if you have anything else that you can make up. Okay?
Hey, Professor, are you gonna send that thing in today or tomorrow?
What was that?
You said you were gonna put something on Canvas like practice problems or what it's gonna cover.
I'll send you the list like right now, as soon as I finish.
Okay, all right, perfect.
And the quiz is Tuesday, this coming Tuesday?
The quiz is for this Saturday. Do you need some extra time?
Maybe, because I have a class in 15 minutes, so I don't know, like, when is the quiz going to be released?
The quiz is already there, and it is due Saturday.
Okay, so we have a few days then.
Yes, you do. I just want to kind of, finish with that this weekend and focus on this. That's why I have today. Okay? All right, guys. Then I'll see you next time.
Oh, and one other thing. I went to your office hours. I want to make sure. Is your office hours from 2 o'clock to 3:15, or is it 2 o'clock to 3 o'clock?
2:45.
Oh, 2 to 2:45.
Yeah.
So it's less office hours than before then.
It's the same.
Oh, I thought it was an hour and 15 minutes.
No, it was 1:30 to 2:15 before.
Oh, okay.
Yeah.
Oh, my bad, because that would explain it. Because I tried joining your office hours, but it was like 3:02 p.m.
Oh, I see. Yes, I missed. But yeah. So if
Okay, thank you.
Okay.
Bye.
Bye.